Today we're going to continue our part 2 of verbal and applied problems with our quadratic equations. You can use the same note packet from yesterday, but we're going to use the data 514 as well. So this is what they looked like. We filled out problems 1 through 4 yesterday. We're going to pick up today with number 5, and this is the rest of the packet. Yesterday we covered basic number problems and consecutive integer problems. Today we're going to look at ratio and area problems. These are all problems that we did visit once before when we had our word problem unit. Now we're just integrating the quadratic equations into it. So for number 5, it says the ratio of the measure of the length and width of a rectangle is 5 to 7. When they talk about ratio, whatever's mentioned first, 5, pertains to the dimension they mentioned first, which is length. The second dimension, 7, goes with width. It was mentioned second. So we want to maintain that order. What you have to know is that when you have ratios, we talk about parts. X would represent one part of this total area. But the length is 5 parts. So we're going to use 5x to represent the length. And the width is 7 parts. So 7x is the width. From there, we're going to start with an area formula for a rectangle, which is length times width. You can use base times height, side times side, and we're going to sub in what we know. So we know that the area is 1,715 feet, and we're going to multiply our dimensions for length and width. Make sure you put parentheses around these so that we don't lose a coefficient or an exponent. So this will give me 35x squared, which makes this a quadratic equation. Now we could move 1,715 over and then pull out a GCF, but we can make that happen if we divide both sides by 35 first. So when I do that, now I have x squared equals 49. If I square root both sides, we get that we have a factor of positive and negative 7. Now, we cannot have the dimension of our rectangle be negative. So we do acknowledge that there's 2 roots, but we're going to disregard or reject the negative root, and we're going to sub in 7. So 5 times 7 is 35, and 7 times 7 is 49. So writing our conclusion, we know that the dimensions of our rectangle are 35 feet by 49 feet. In example 6, we're working with a parallelogram. It says the base measures 7 centimeters more than its altitude, which is a height. And then they're providing us the area. So let's define our terms. X seems to be the smallest dimension, so that's our altitude. And then the base is 7 centimeters more, so x plus 7 is our base. A parallelogram is a tilted rectangle, but the formula is still base times height or length times width. We're going to sub in all the parts that we know. We do know the area. Make sure you put the quantity of x plus 7 in parentheses, and then we're going to distribute. And then knowing that it's quadratic, I'm going to subtract 30 to get all my terms on the same side. I can factor using product sum. I want to multiply to negative 30 and add up to 7. 3 and 10 are good candidates. So we have the quantities of x plus 10 and x minus 3. I'm going to set each binomial quantity equal to 0. I'm going to start with x plus 10. This tells me I have a root at negative 10. We're going to reject this option. Even though it's a correct solution, the length of our rectangle or parallelogram cannot be negative 10. The other root, though, is at positive 3, and this will make sense in the context of the problem. So subbing into my let statements, I have a height of 3 and a base of 10. So in my conclusion, the dimensions of the parallelogram are 3 feet by 10 feet, and that should be centimeters. In example number 7, this problem is a little trickier. It says the length of each of a pair of parallel sides of a square. We're starting with a square, but we're going to change the dimensions to make it a rectangle. So one set of parallel sides will be increased by 2, and then the other 2 sides will be decreased by 2. I'm going to start by defining x as the original side of the square. If I increase one side, I'll have a new length. And if I decrease the side, I'll have a new width. And it really doesn't matter who you call length and width. The area is 32 square meters. So we'll start with our formula. I'm going to sub in 32 for the area, and then I'm going to use the new dimensions of my rectangle. I'm going to go ahead and distribute. Positive 2x and negative 2x will cancel out. And then I'm going to move the 32 over to join the constant of negative 4, and I have x squared minus 36 equals 0. This is the difference of perfect squares. So I know that the values of x are both positive and negative 6. Again, I'm acknowledging both roots, but the length of negative 6 would not be the length of a side of a square. So we're going to use the positive root, and the original length of my square was 6. I put feet, but it's really meters. In the last example, we're working with a right triangle. We did visit right triangles back in the unit where we looked at square root radicals, and we used the Pythagorean theorem there. So this says the hypotenuse of a right triangle is 1 inch longer than one leg and 8 inches longer than the other leg. This one I thought was a little confusing to set up. One of my legs is just x. The hypotenuse is 1 inch longer than one leg and 8 inches longer than the other leg. What I actually did was set up the hypotenuse 8 inches longer than my first, but it's 1 inch larger than my other leg. So these dimensions make sense. The other thing we have to recall is the Pythagorean theorem. C squared equals a squared plus b squared. C always represents my hypotenuse, which is my longest side, and it's across from my right angle. I'm going to go ahead and sub in my dimensions. Don't forget you need parentheses. Because I have so many quantities that are squared, I'm actually going to expand so that I can distribute properly. So on the left, I should have 3 terms. This is a perfect square trinomial. The original x squared, I'm just going to bring down, and then this is also a perfect square trinomial. And now I'm going to start to combine like terms and move things from side to side. So I combine the 2x squareds, and you want to move everything so that your quadratic term is positive. So I'm taking the perfect square trinomial on the left, and I'm subtracting all those terms to put them on the right. And this is the resulting quadratic. It is simple enough to use the product sum method of factoring. So factors that multiply to negative 15 and add up to negative 2. And I have x minus 5 and x plus 3. So for my first root, I have a solution at 5. That seems to make sense with this problem. The other solution is at negative 3, and that one will not make sense. I don't have the length of a side of a triangle at a negative. So we'll go with 5 for the one leg, and then we'll sub in. I have a leg that's 12 and a hypotenuse that's 13. So I'll set up my conclusion. This is really called a 5, 12, 13 right triangle. This is a Pythagorean triple. Tonight's homework is number 116. You're going to do the circled problems. I encourage you to write all of your let statements and then draw a picture if you need to. And there will be other problems on the homework sheet as well. I would encourage you to do this on separate paper or on the blank sheet that's on the back of the paper copy. If you have any questions, please make sure you contact me and I'll be happy to help you. Have a great day.